In this video, we're going to look at a different way for conceptualizing how a regression model changes when we add variables. This time focusing on the variance in the outcome that we're able to account for, our R squared. We'll do that using what are called Venn diagrams. Venn diagrams look at the relationship between the variance shared by variables in the model and can also be very helpful in understanding the concept of statistical control. To illustrate Venn diagrams, let's return to our example of grades, our outcome variable, and school quality. Now, as this suggests, in a Venn diagram, variables are represented as circles, all the same size. The circle represents the total variance of the variable as a percentage, not in terms of any actual numerical value. If two variables are correlated, it indicates, right, that they share some variance. Remember back to correlation. R squared is the proportion of the variance the two variables share. In Venn diagrams, we illustrate this by having the two circles overlap by the same amount that's equal to that shared variance. So if grades and school quality are correlated, the two circles will overlap with the proportion of each circle overlapping equal to the R squared. As a result, if the correlation between school quality and grades is 0.5, the R squared would be 0.25, and the overlapping area in the Venn diagram would be equal to 0.25, reflecting 25% of the variance in each variable that's shared with the other. Now, what's nice with Venn diagrams is that they clearly illustrate this overlapping variance between two variables. In fact, the description of overlapping variance is so clear in Venn diagrams that you'll see that language used all the time when people report statistical results, even if they're not using a Venn diagram. Overlapping variance, right, is just that variance that two variables or more variables share with each other. Now, let's keep going with this example. If the overlapping variance is equal to 0.25, we know that the remaining variance in grades is equal to 0.75, right? They add up to 1 or 100%. Now remember, again, these are proportions of the variance, right? This visually, though, tells us that there's still a fair bit of variance that can be accounted for by other variables. Now, what happens if we add a second predictor variable, study hours? Let's assume that study hours is correlated to both grades and school quality. What would the Venn diagram look like now? Now, it gets a little more messy and complex, so let's clean up this figure and start over. So we'll start with grades, with the circle again reflecting the variability in grades. Some kids have high grades above the mean, some kids have low grades below the mean, right? And then here's study hours reflecting the variability in how many hours kids study, and school quality reflecting that variability in school quality. As we see, all the circles overlap, reflecting the fact that all three of these variables are correlated with each other. For example, the shared variance between study hours and grades is here, reflected in the areas labeled A and C. This area is equal to the squared correlation between study hours and grades. Similarly, the variance between school quality and grades is here, reflected in the areas labeled B and C. This area is equal to the squared correlation between school quality and grades. Finally, the shared variance between study hours and school quality, our two predictors, is reflected in C plus this area D. Now notice D is the overlap, that variance that study hours and school quality share with each other, that's not related to grades at all. And notice that C is the variance that's shared by both study hours and school quality that's also shared with grades. It overlaps all three of our variables. Now, focusing on the variance in grades for a moment, notice that the area A, C, and B as a group reflects the variance in grades that's related to or accounted for by study hours and school quality as a set. And if you think about it, you may recognize that this is the multiple R squared, right? The variance in the outcome that's related to our set of predictors. With Venn diagrams, you can literally see how that total R squared is equal to the sum of these overlapping pieces of variance. Now finally, the variance in grades that's not related to any of our predictors is reflected in this area, which we'll label E. That's equal to 1 minus our R squared. Now, if you think about it, Venn diagrams do a great job of illustrating statistical control. Look closely at A. It's the variance in grades that's only shared with study hours. That's because A doesn't overlap with school quality at all. It's just study hours and grades. And remember, that's one way that we described statistical control, the effect of a variable after removing the effect of all the other variables. That's exactly what A is. A is what's left over. It's that leftover effect of study hours on grades after we've removed the effect of school quality. It's like we've taken a bite, right, out of the effect of study hours. A is uncorrelated with school quality. It's completely unrelated to it, right? It's that part of the variability in grades that's solely and uniquely related to study hours. Similarly, the variance in grades that's only shared with school quality is equal to B. That's because B doesn't overlap with study hours at all. It's the effect of school quality on grades, removing or controlling for study hours. B is also then uncorrelated with study hours, right? It's that part of the variability in grades that's solely and uniquely related just to school quality. Now, that leaves us with C. C is that special place, that special space, that special variance that overlaps all three variables, both predictors and our outcome. Now, remember, A, B, and C combined are the R squared, the variance in the outcome that's explained by our set of predictors. So A, B, and C reflect pieces of that R squared, pieces of that overall or total effect of our regression model. In future videos, we'll see that researchers spend a lot of energy worrying about which predictor should get credit for each of these pieces. Now, in that regard, the variance reflected in A is pretty straightforward. As we saw, it's the unique variance in grades that is only shared with study hours. It's the effect of study hours controlling for school quality. So study hours should clearly get credit for A. Similarly, the variance reflected in B is also kind of easy, right? It's that unique variance in grades that's only shared with school quality. It's the effect of school quality controlling for study hours. So not much controversy about giving school quality credit for the B variance. But who gets credit for C? That's a challenge, and it often comes down to theoretical judgment. One researcher may say, I think it's the kids studying more, so study hours rightfully deserves the credit for that C variance. While another researcher says, you're crazy. Clearly it's the better school quality that leads to kids studying more. That variance rightfully belongs to school quality. Now, okay, they may not say you're crazy, but it comes down to theory. This is why, as a researcher, you need to know your literature. What does the research evidence say? You don't want to be that person who says, I believe the overlapping variance is due to this variable, and have all your colleagues say, what are you talking about? Clearly the research shows that it's due to that variable. I've seen that happen, and it is not pretty. It's also why you need to know your statistics. How do you analyze and interpret the data in a way that gives the correct variable credit for that overlapping C variance? Sadly, you'll see people think that they're giving one variable credit for the overlapping variance, and in fact, statistically, they're giving the credit to a completely different variable. Ouch! At this point, you're probably wondering, now, how do you give credit to one variable or another variable when looking at things like variance? And we'll get to that later in some future videos. But for now, appreciate the quandary that this creates at a conceptual level. There's a portion of the variance in grades that's related to both predictor variables. How do I decide which variable is responsible for it? Which one, if either of them, gets credit for it in my analysis and in my interpretation and in my conclusions? We'll come back to that who gets credit for C question a lot in future videos. But for now, that wraps things up here. Okay? Take care. Bye-bye.